Good afternoon, my name is David Summerland. I'm one of the founders of the Rais technology and a co-inventor, and I'm going to take you through on this video of the key benefits and USPs of the Rais and rub technologies for this fantastic little IC. Here you can see the Rais IC itself, this tiny little square. And what we've done is we've put the Rais IC mounted onto this little dual inline carrier. This allows it to be plugged into the eval board and replaced or changed as required. And here you have the eval board itself, which is oversized deliberately so we can use these dual carrier boards and so that we can play around and scope with the actual application. In reality, this would be the size of a 10-cent coin for a finished application 8-watt driver. Here we have the eval board wired up. We've got mains in, coming into channel 1 on the power analyzer, and that power comes into the board, so channel 1 is measuring the input power and current, and then the output of the eval board goes back into channel 2 of the power analyzer, the output of which is connected to the LED. This allows us to measure the input power and output power and determine the eval board efficiency live. In terms of the connections, we've got an oscilloscope connected to channel 1, which is connected to the output of the Rais IC, and we have channel 4 of this oscilloscope connecting to measure the current coming out of the output pin of the IC. If we go to the analyzer, we can see it's measuring the efficiency at 89%, 230 volts in, input current of 23 milliamps RMS with a peak of 43. Input resistance 9.6k and a power factor of 0.95. On the output we're driving a 50 volt LED, which is a very nice LED to drive, being low current, roughly 4.6 watts, 102 milliamps. And this is an application where you would use the Rais IC just using a standard bridge rectifier on the output. You wouldn't need our secondary rub IC. Here we're looking at the oscilloscope traces of channel 1 and channel 4 described for the connections on the eval board. You can see the current here is the blue trace and the voltage here, and down here these are zoomed in. So here's the zoom window, and down here is that window zoomed. You can see here that the output has a lovely soft slew rate, which is good for EMC, and that the current marked by these cursor points here is crossing 0, and then the FET turns on just after that point, so that we don't actually switch any current, we don't actually switch any voltage. The voltage is already at the point where it needs to be by the time the FET turns on. It's one of the key reasons why it's so efficient. As well, you'll notice a very, very low current that passes through the IC despite the fact we're switching a higher current on the output. So if you have a quick look at the board now, remove the current clamp so you can see what's going on. Basically what you've got here, Rais IC itself, the diode bridge on the output, which is where the rub IC would connect in low voltage applications, L1 and L2 as the resonant components with C1, as you'll see described in data sheets, and L3 which is an input inductor, which we recommend as a ring inductor to absorb any shocks from the triac. If it is that you want to put different voltages on the board, down at 20 volts, and see what kind of powers we get, there is an auxiliary connection here where you can connect an external 15 volt DC supply, and then you can take this AC supply right down to 0 and see how Rais reacts with the different voltages. Okay, now we have that exact eval board shown in a finished end application. This is it fitted inside a lamp. You can see how small that actually gets. So we've got basically what was essentially that 5-watt lamp. It's connected to a standard triac dimmer. We're going to show a range of these dimmers. This is the first one, of which is the easiest to be attached to. And if I turn it on, you'll see it's got an immediate pop in. There's no delay. That lamp is straight on, even at the dimmest settings. And then you'll see as we turn it up, and gets brighter and brighter. You can see that the Rais is forcing the conduction all the way through the waveform. You will see a spike here when it turns on, That can easily be reduced in amplitude by using the correct ring inductor and inrush. At the moment we have a very small standard drum inductor on this. It's better to use an iron powder ring core to reduce that spike, and we've also got a phase by phase soft start on the rub IC which can be used to also help reduce the inrush. Here we have a trailing edge dimmer. See, Rais again isn't concerned what kind of dimmer is connected. See the current waveform being drawn again, and again I can just play with the dimming whatever I want and it's fine. You'll see right down at the lower levels, in order to keep the dimmer running, you'll see the load resistor kicking in just to make sure that the dimmer keeps its auxiliary power going, which is required for it. Here we've got an example of a particularly hard dimmer to work with. These are ones where you have some kind of processor or intelligent dimming. Generally these ones can take quite a lot of auxiliary power, it could be up to 3 watts, which could fool most LED lamps into coming on when they shouldn't. And also they tend to have very high power drive capabilities, so the minimum load does go up. Our claim at Rais is that we work with 100% of dimmers at some particular power, pretty much the same as tungsten lamps do. The idea is that you've got to match the load of the lamp to the load of the dimmer, but with Rais that's at a vastly reduced power level, which is important with LEDs being so efficient. So an example of how this can go wrong: if I dim this lamp down to a low level, you'll see a slight glimmer there that's happening at the lower level. And a way around this to make sure that it works at all the power points on the dimmer. I mean, it isn't bad, but you know, if you want 100% loading correctly of this dimmer, and what we would do is simply connect the second lamp. So we've got a little bit more load on the dimmer. And now when we dim this down, you can see that they're completely stable and they're doing the low level dimming perfectly. You need to know, in this particular application of lamp, there is absolutely no electrolytics whatsoever. And this is why you'll see a little stage jump each time the dimmer moves a level. That's not the lamp flicking, that's the actual dimmer moving from its next step to its next step, because it's a digital type dimmer. Here we have an example of a European dimmer. Siemens, one of the most common dimmers in Europe. Again, a lot of LED lamps can have an issue working with these, but we'll show you that there's no issue at any one point. Here's the minimum dim level, nice and dim, it popped in straight away. You'll notice that when it's off, the lamp is off. There's no glimmer whatsoever coming from the LED, there is no power. We can show you that, and you can see there's nothing. This was the same for all dimmers. The Rais circuit, or the Rais IC, is able to make sure that when the dimmer is off, the lamp is off. So immediate popping, and again, nice dimming profile. Something else to note about dimmers when they're being used: they can have really ropey waveforms. Every single one is different, and it's a common method out there to regulate the power coming in completely and then monitor what the dimmer is doing, or try to monitor it, and then get the output to predict what that monitor is doing. And you can do this successfully for 100, 200 dimmers, and one day you'll come across one that acts in a slightly different way, or it's installed in a different application, or the building electrics are different. And that, on that day, in that building, will cause you an issue. The beauty of Rais is that it transfers the input power to the output power in the same way that a lamp uses that power. And therefore we don't have the issues of trying to predict what the dimmer is trying to do. We just transfer that power and make the lamp, our LED lamp, or any LED lamp using Rais, act exactly the same as a normal lamp would act. You can see how horrible it is to try and predict that waveform.